Alright, so this is going to be a quick reference for Newman projections. Essentially what Newman projections do is show us a skeletal structure of a organic compound in 3D. So the same structure that we were seeing before has these implied hydrogens, and basically every sp3 carbon, so these will have this tetrahedral shape. So we can look at them in 3D because they have these tetrahedral shapes. And what we do is we pick a direction that our eye wants to look at it in. So in this case, the eye is looking through this carbon and at that carbon. So we're looking essentially down this bond. Things on the right-hand side of this cyclops, there's his right shoulder, will be the wedges, and his left-hand side, that was his right, his left-hand side, which we can't really see, will be the dashes. So, as we look down this bond, what we draw first is the first carbon we see, and the way we represent that is a dot. Then we draw our legs for it, and in this case we have two legs going down. One of them now is in purple or pink, I'm not sure, I'm colorblind, but that's our two legs and our one leg up. Now, the ones that are dashing ledges will go to the left or the right of the center, and the one that is a non-dash or wedge will go straight up in all cases. So this time, in this case, it's pointing up, the back one is pointing down, but so that there is there, and since when looking at this way, the things coming at us on the screen are the dash or wedges, excuse me, and they will be on this guy's right hand side. So we're going to put those on the right. So that right is that one right there. And you can fill these out like that. Now we've taken care of the first carbon, let's take care of the next carbon, the back, which is a big circle, and that's how we represent it. I know in 3D, when we look at things, the things that are further away are actually smaller, but in Newman projections, we're going to draw them bigger. So we're drawing this back carbon as a giant circle, even though it's in the back. And this first carbon is a tiny circle, even though it's in the front. So we do the same thing. There's two legs of this up, so we draw our two legs up, and there's one leg down, so we draw our other leg down. And then we fill them out, figuring out what's on this guy's right-hand side, and we put those on the right-hand side. What's on his left-hand side, we put that on the left-hand side, and the thing going straight down, we put it straight down. So fill that out, methyl's down, there we go. So now there are different positions. This is the anti-staggered. Basically, I'll get more into what staggered is, but when you have these large groups, in this case are methyl, and when they're the furthest apart, we call that anti. So we'll get these two big things as far away as possible, that is anti. When looking at Newman projections, we can actually rotate about that single bond right there. So in this case, I'm going to rotate the front carbon, and that's what it looks like. So that's what Newman projections allow us to do, is to rotate these molecules. So now, there are two types of positions, staggered and anti, or staggered and eclipsed. Eclipse is when you have things overlapping like that. When things are eclipsed, they're really close together and they start to collide with each other in 3D space. Their electrons repel, and that's not very stable and causes high energy. So you don't like eclipsed. There's another thing. This eclipse here, where we have a methyl on top, so the methyl here, overlapping with a hydrogen behind it, that's not so bad because one group is big and one small, so there's not a lot of overlap. But when we have an eclipsed and these two large groups overlap, that is very bad, very high in energy, because there's a lot of collisions and repulsions. So there are more favorable eclipsed, such as that, and less favorable eclipsed, such as that. But then we have staggered, and that's when we have an alternating kind of pattern, like that or like that. And when we have an alternating pattern, things aren't so close together. They're still kind of close. There's still some proximity between those two, but it's not so bad. And it's relatively low in energy compared to all the eclipsed positions. However, there is a most optimal anti-position, and that is, or staggered position, and that is the anti-position, when we have the large groups further away. And that is the energy relatedness to Newman projections. So we'll see that one more time. We'll spin the back carbon this time. There we have an eclipsed, not so bad. We have a staggered, it's okay. Now we have a really bad eclipse because we have two large groups overlapping there on the top. Then we have a staggered, that's pretty good, but then we have our most optimal staggered, which is the anti-staggered, and that is Newman projection.